Hello all, my name is Minna and I'm giving a short presentation about efficient and interactive human-robot collaboration. Starting from the industrial revolutions, if we look for the second revolution, it started because there was a need. It was the automation of the slaughterhouse. And the requirement for the automation was that for the speed and ergonomy, also there were no refrigerators at that time. In order to increase the productivity, we had to invest on the automation. And now we are moving to the fourth industrial revolution, where we actually have smart machines, connected machines, and we are relying quite much on data processing and reasoning. What we look for the future, the engineering dream is that we have automation and artificial intelligence. For the general population, this could be referred as a nightmare. But in the future factory, if our dream would sort of realize the vision, we would only have the robots, artificial intelligence, and the management, or the middle management, where the man is responsible for feeding the dog, and the dog is responsible for not letting the man touch anything. We would rely on the robotics and artificial intelligence. However, that's not realistic. We are moving also to the lot size 1, meaning that we have highly personalized products and we can't simply automatize everything. So now it's the dawn for the human-robot collaboration. This is something what we currently have. For example, the safety eye from Builds is only commercial application on allowing humans and robots collaborate. The problem is that it's a very static system, and what we are looking forward is that how we make this more interactive. So our solution for allowing the humans and robots collaborate efficiently. So first we are building the coexistence. They are working on the same product at the same time. We have to organize or create the safety system that allows this collaboration to happen. And then we can look for the productivity. This was realized with the depth cameras, so we are supervising the volume where the robot moves, and the volume is increasing, or the robot workspace is increasing, faster the robot goes. And we are using the projector to notify the human where the robot is actually going. And also using the projector and the depth camera for realizing the human-machine interface, where the human is actually making the base for the work.
Thank you.
Thank you.
Precise.
Hello, my name is Andrei, and today I'm going to speak about 5 schools of thought for building intelligent systems. So, starting with intelligent or intelligent systems. So intelligence could be defined as an ability to collect and apply the skill. And here are 2 words are highlighted: collection and application. For collection, we need to represent somehow those concepts what we collect, and then to apply, to turning the knowledge into know-how. So some other steps are needed. And for making those steps, we can have different approaches, or in other words, schools of thought, originating from one can say Greece. So here is the painting by Raphael, and depicting Greek philosophers. Platon and Aristotle are in the middle, in the lower left corner Pythagoras, and some other figures. On the stairs in the middle lying Democritus, so the founder of the school of cynics, which denied all those smoke of the reality, but trying to see through. Anyway, there are different approaches, and when we speak about technology, we can find or say about those 5 schools of thought. Which can be symbolists, connectionists, evolutionists, statisticians, and interactionists. If we speak about application to the robot, depicted in the upper right corner, about symbolists, in order to reach certain position, you need to manipulate symbols. And what are those symbols? Those symbols are trigonometry. if you speak about kinematics, knowing how to reach something, and trigonometry has certain laws. Then connectionists, one particular example could be recognition of the silhouettes, and basically some of the machine vision applications are there. Then evolutionaries, one example, genetic algorithms finding the fittest solution, so adapting. Statisticians seeing the whole picture, finding unknown features or which we didn't have previously the knowledge. Interactionists, it's not only important the symbols that we manipulate, how they are represented, but what is the message and what communication pattern we use, and all of these should bring us to the holistic view of joining different methods from different schools of thought for being able to build truly intelligent system. And what is the right balance? We are still in search, and I'm inviting you to discuss at this table too. Thank you.
My name is Arun, and I'll be talking about how approaches like deep learning and more classical approaches like model predictive control and convex optimization can be combined to solve challenging robotic applications. So classical methods have more theoretical mathematical guarantees. Deep learning, on the other hand, works well with less assumptions, but it's kind of black magic. We don't really understand what's happening there. So our aim is to find a middle ground and solve problems with that. So the first application that we're looking at is related to multi-vehicle coordination with applications to warehouse automation. So in the figure that you see over there, so circles represent the robots and the straight lines represent the paths of the robots. The task is to coordinate the vehicles along those paths without collision. Now this has obviously applications to autonomous intersection management, warehouse automations. Now this problem has two components. So one is the priorities, that you have to figure out which way robot goes first, second, third, and so on. And once we have figured out the priorities, we have to figure out how the robot should accelerate, deaccelerate, move. Now it can be shown mathematically that if you figure out the priorities, then the motion part can be framed as a convex optimization problem. But then how do you figure out the priorities? So what we are doing is that we are trying to do a deep reinforcement learning framework to kind of learn a good heuristics for priorities. That means given a context, we'll figure out the priorities through the deep RL heuristics and then use convex optimization to solve the coordination problem. The second application that we are looking at is how to use the neural network learned dynamics over model predictive control. For example, in the Rolls-Royce talk, the surface vehicles dynamics, fluid vehicle interaction cannot be modeled accurately. So we can use neural networks to model the dynamics and then do some theoretically sound model predictive control over that. Now this is not exactly a new idea. It has been done in the past, but kind of abandoned because MPC over neural network dynamics becomes really difficult. So what we are doing is we are trying to innovate at the level of the optimization. We are coming up with better non-convex optimization techniques which can handle the underlying optimization of this MPC with learned neural network dynamics. And I'll be at booth 3 if you want to see some current results that I have. Thanks.
Ladies and gentlemen, I am Dr. Borja Ramis, and I'm today here for talking to you about my research in 3 minutes. My research is on knowledge representation and reasoning machines, which is related to the field of artificial intelligence. Particularly, I am working towards the provision of knowledge to machines. Some of you might think that this is new, but it's not. The capture of human knowledge and representation of such knowledge into machine interpretable manner is something that has been done during the last years, actually decades. One of the reasons why we are doing this is because even though we are able to implement really complex algorithms and behaviors for controlling machines, machines are not able to understand what they are doing. If we bring understanding to machines, they will be able to know what they are doing. And this is what we want to do in order to create intelligent machines. So this sounds interesting, but why we need all of this? Let me give you one fact. The cost of configuration and integration of machine software can reach up to 5 times the cost of it, 5 times more. The provision of knowledge to machines permit the reconfiguration and integration of knowledge in order to adapt and evolve to, for example, mass customization. Let me put you an example. Imagine that you are running certain process and suddenly, due to client demands, this process must be changed. Actually, as usual, imagine that this change must be done fast enough in order to meet the requirements of the client. If we have here people from the business sector, they know that this kind of situation, this kind of changes are really costly in time and hence in money. What we can do, we can create knowledge models that are understandable for the machines and systems that are involved in the production. If these systems are aware about what changes they must do and about the demands, they will be able to reconfigure themselves and adapt to the problem. This is what knowledge representation and reasoning machines is about, creating intelligent systems that can reconfigure themselves on demand and at runtime throughout the understanding of knowledge-based models. If you want to know more about this, some cases and applications, visit me after this session to stand number 4. Thank you.
I'm Aref and I'm gonna talk about invertible nonlinear dynamics for deep learning. We are in the Department of Automation and Hydraulic Engineering, and I'm representing our research team with the achievements that we have recently. So what does invertible blah 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 deep learning means? Deep learning is supposed to be an eye-catching term recently, especially after 2014, where it beats human perception. But when we want to apply that for our mechanical systems or so-called cyber-physical systems, we used to have many challenges. What we are focusing is that when we have a complex system that has nonlinearities, instead of looking end-to-end, such as the recently developed autonomous and smart machines, we try to just break it down into complexity of subsystems. And then each subsystem can be dealt with learning of deep learning methods. And then we can manage with a lot of data that we used to have because of a real-time control system or because of health monitoring that they are already gathered on the system. Usually these kind of data, they have some challenge that they are a lot of data, but it needs to be big, useful data, not just big data. And we worked on identifying good data for training, and at the same time, we have traditional methods to compete with these methods, so we can combine them together to have better understanding of the nonlinearities of the system. To overcome this issue, these kind of systems, they are in the laboratories, but what we want to do is to have millions of these systems, so we gather this gap between need for big data and the actual data by accurately simulating our machines on virtual environments. Then what did it work? At least in 2 cases, by almost the same method, we have been able to identify degrees of freedom of working machine by use of IMU sensors with their noisy data. And at the same architecture, we were capable of identifying dead zones on the actuators. Just by learning of input and output signals, we were able to improve the accuracy of dead zone prediction from 70% that used to be by the classic methods to the 90% accuracy in the entire tests. Thank you.
Hello, my name is Tomi Krogerus and I'm coming from the Laboratory of Automation and Hydraulic Engineering. And in that lab we have a small group presented in the upper corner. So approximately 5 persons at the moment dealing with data analytics of industrial systems. And we are doing a lot of collaboration with Åbo Academy IT department embedded systems lab. So our main objective is to develop methods for predictive maintenance so that we can optimize service actions. So what we want to actually do is to avoid unnecessary technician callouts. We want to achieve zero downtime. We want to provide support for the decisions for the operator. And how we do this, we use machine learning from simple regression models to deep learning. A lot of work has to be obviously before. So most of the time usually goes for data cleansing, feature extraction, compressing the data, and after that, the classification and different statistical methods that we use. And the data that we are dealing with is usually sensor usage and maintenance data. And goal is to optimize the cloud and edge cooperation so that we have a so-called distributed AI. And the systems you can see there, we have been working with our elevators, wheel loaders, cranes, diesel engines, and so on. So here is one example case of a method that we developed for vibration signals for monitoring the system health. So multiple vibration features extracted from the vibration data. We create models from the healthy data, and based on the models and the data, we can estimate our health, the probability of our system being health. So what we actually gain here is a robust fault and anomaly detection. So we can, for example, detect increased vibration levels, reduced comfort, and calculate some statistics out of the fleet. And obviously, why this has to be robust, why we use only healthy data, that usually we are lacking the faulty data, or it's really sparse amount. So the difficulty lies on that, and not to get these false alarms so that we don't send technicians on sites for weighing purposes. Some references ongoing. We have an open project still next year